Welcome to one of the deepest mysteries in physics, the quantum measurement problem. A quantum system exists in multiple states simultaneously until the moment we measure it. But what exactly counts as a measurement? Let's begin with the foundation, quantum superposition. Imagine flipping the coin. Classically, it's either heads or tails, even while spinning in the air. A classical coin is either heads or tails at every moment, even if we don't know which. But a quantum coin exists as both heads and tails simultaneously until measured. This is superposition. Mathematically, we write the quantum state psi as alpha times state 0 plus beta times state 1. The coefficients alpha and beta are complex numbers whose squared magnitudes sum to 1, ensuring probability normalization. Consider an electron's spin. Before measurement, it exists in a superposition of spin up and spin down. The electron simultaneously points up and down until we perform a measurement. Now comes the mystery. What happens during measurement? According to standard quantum mechanics, measurement causes the wave function to collapse into one definite state. Before measurement, the system is in states A and B. After measurement, it's definitely in state A, for example. The superposition alpha A plus beta B collapses to just state A with probability alpha squared. But here's the deep problem that has puzzled physicists for nearly a century. What exactly counts as a measurement? When does this collapse actually happen? Does the measuring device need to be conscious? Or is any interaction enough? Is collapse triggered by the detector, the observer, or somewhere in between? Let's examine the equation that governs quantum evolution. The Schrödinger equation, I times h bar times the time derivative of psi equals the Hamiltonian operator acting on psi. Here's the key issue. This equation is completely deterministic and reversible. It never produces collapse. The Hamiltonian is kinetic energy p squared over 2 meters plus potential energy v of x. The Schrödinger equation smoothly evolves superpositions into other superpositions. No collapse occurs naturally. As time progresses, the wave function spreads and evolves, but remains in superposition according to the Schrödinger equation. So we have two contradictory processes in quantum mechanics. Smooth unitary evolution between measurements versus sudden collapse during measurement. This is the measurement problem. The famous double-slit experiment perfectly illustrates this mystery. An electron source shoots particles through two slits toward a detection screen. With both slits open, we observe an interference pattern, proving the electron went through both slits simultaneously. The pattern shows bright and dark bands, characteristic of wave interference from both slits. But if we place a detector to measure which slit the electron goes through, the interference pattern disappears. With the detector at one slit, we get two simple piles of electrons, no interference. The act of measurement changes reality. Without measurement, the electron is in a superposition, 1 over root 2 times slit 1 plus slit 2. Measurement forces the electron to choose. It went through slit 1 or slit 2, destroying the superposition. Modern physics offers a partial solution called decoherence. The key insight is that no quantum system is truly isolated from its environment. Every quantum system interacts with countless environmental particles, photons, air molecules, thermal radiation. The system state psi becomes entangled with the environment state phi, creating correlations. Let's look at actual numbers for how fast decoherence occurs. The decoherence time tau is approximately h bar divided by lambda squared times n times k dash b times t. For a dust particle 1 micrometer across an air at room temperature, let's calculate. The decoherence time is about 10 to the minus 40 seconds, essentially instantaneous. This explains why we never see cats in superpositions of alive and dead. Decoherence is too fast. Decoherence creates an effective boundary between quantum and classical behavior based on environmental interaction strength. However, decoherence doesn't fully solve the measurement problem. It explains why we don't observe macroscopic superpositions, but not which outcome actually occurs. Despite decoherence, fundamental questions remain unanswered. Does the wave function really collapse into one outcome? Or do all outcomes exist in parallel universes? The many-worlds interpretation says both outcomes A and B occur, but in separate branches of reality. Different interpretations of quantum mechanics give fundamentally different answers to what happens during measurement. Copenhagen interpretation says collapse occurs. Many worlds says the universe branches. Both match experiments. Recent experiments with weak measurements reveal subtle quantum behavior. A weak measurement is a very gentle interaction that barely disturbs the quantum system. A strong measurement forces collapse to A or B definitively. A weak measurement causes only a tiny change epsilon, preserving most of the superposition. By performing many weak measurements, we can track the average quantum trajectory without forcing collapse. Weak measurements allow us to observe quantum trajectories that would be destroyed by strong measurements. When exactly does classical behavior emerge from quantum mechanics? The correspondence principle states that quantum mechanics must reduce to classical mechanics for large systems. In the limit of large quantum numbers, quantum predictions match classical physics. However, the boundary between quantum and classical is fuzzy, not a sharp dividing line. There's a mesoscopic regime where systems show both quantum and classical features simultaneously. Examples include superconducting circuits, large molecules, and quantum dots. These systems have sizes from nanometers to micrometers, bridging quantum and classical worlds. Continuous measurement can freeze quantum evolution through the quantum Zeno effect. Named after Zeno's ancient paradox, if you check an arrow's position continuously, it never moves. In quantum mechanics, if you measure a system frequently enough, you can prevent it from changing states. The probability of no transition after n measurements separated by time delta t depends on the transition rate gamma. As n approaches infinity and delta t approaches 0, the probability approaches 1. The system freezes. Rapid repeated measurements effectively freeze the quantum state, preventing natural evolution. This effect has been experimentally verified using trapped ions and other quantum systems. Some physicists argue measurement is fundamentally about information transfer. The information theoretic view says measurement is when information about the quantum system becomes irreversibly recorded. Entropy S equals minus k-b times the sum of pi natural log of pi, measuring information content. Before measurement, information exists in quantum correlations, not definite classical bits. Measurement transfers quantum information to classical information that can be copied and stored. After measurement, information becomes classical bits that can be copied, stored, and communicated. Quantum information cannot be cloned, but classical information can be copied infinitely. Some physicists propose that wave functions spontaneously collapse without measurement. The GRW theory proposes that wave functions undergo random spontaneous collapses at a very low rate. The collapse rate lambda is about 10 to the minus 16 per second per particle. For a single particle, collapse essentially never happens over observable timescales, but for a macroscopic object with 10 to the 23 particles, collapse happens millions of times per second. This explains why microscopic systems stay quantum, while macroscopic objects are always classical. In these theories, collapse is a real physical process, not just something that happens when we look. Modern experiments are pushing the boundaries of quantum behavior. Scientists have demonstrated quantum interference with molecules containing over 2,000 atoms. These molecules have masses around 10,000 atomic mass units. These experiments push the boundary between quantum and classical, testing where superposition breaks down. Some researchers aim to create quantum superpositions of microscopic living organisms like tardigrades. Would this resolve the measurement problem? Or just push it to an even more mysterious level? The measurement problem has profound philosophical implications. Does reality depend on observation? Or does the universe exist independently of observers? Some interpretations suggest consciousness plays a special role in collapsing wave functions. Physicist John Wheeler proposed the participatory universe. Observers help bring reality into existence through measurement. In this view, observation and reality are deeply interconnected, not separate. However, most physicists prefer explanations where collapse happens objectively, without requiring consciousness. The measurement problem is crucial for quantum computing. Quantum computers exploit superposition to perform calculations on many values simultaneously. A quantum bit or qubit exists as alpha 0 plus beta 1, unlike classical bits that are 0 or 1. Multiple qubits create exponentially large superposition spaces for quantum computation. But measurement collapses the quantum state, destroying the superposition. 2 to the n states collapse to just one outcome when measured. Quantum algorithms must carefully avoid premature measurement until the computation completes. Environmental decoherence acts like unwanted measurement, destroying quantum computations. Error rates grow exponentially with time over the decoherence time, tau-e. Let's summarize what we know and what remains mysterious. We know quantum systems exist in superpositions that produce interference effects. We know measurement produces definite outcomes with probabilities given by the Born rule. The probability of each outcome equals the squared magnitude of the amplitude. Decoherence explains why macroscopic objects behave classically due to environmental interactions. But fundamental questions remain unanswered after nearly a century. The nature of reality, the definition of measurement, and the existence of collapse are still unknown.